The step response of an RL circuit is the response of connecting a circuit containing an inductor suddenly to a source in here. And in this particular circuit that I will be using, I'm using the Norton equivalent because dealing with currents is a little bit simpler in terms of inductors because inductors opposes the change in current, so the current right before switching and right after switching will be the same. So what I'll be interested in is a couple of things. I'll be interested in the voltage across the inductor, which is a function of time. I'm also will be interested in the current flowing through that inductor, which is also a function of time. But I'll start by finding the current just because it doesn't change before and right after switching, and then I'll utilize the equation of the relationship between the current and the voltage across an inductor to find what VL of t is. So in this circuit in here, we'll close the switch at exactly t0, so the inductor may or may not have initial storage or initial energy stored in it. I'll assume that it does, and we'll go from there. So the way I'll do it is I'll basically say, well, the switch is closed, so I'll have this as my reference point, and I'll figure out what the voltage in here is. I'll write a nodal equation in here. So let me just write this nodal equation. So this nodal equation will tell me you will have negative I of S plus, I believe that will be some sort of a V, which I can just simply call it V. Actually, it is V of L if you think about it. It is VL of T. It's the same V of L that is here. And also in here, plus it's, well, V of L divided by R, because we're writing nodal analysis, and this is typically KCL, so I'll have some current, plus IL of T equals 0. And again, we can either, because I'm interested in figuring out the IL or V of L, so I can either substitute this by its equivalent in V of L or substitute this in terms of its equivalent in I of L. But I'll just basically replace the V of L in terms of I of L just because I want to start by finding I of L. And just as a quick reminder, we have that V of L of T is just simply L, and that's DIL of T divided by I of T. And of course, based on this here, the passive sign convention tells me that you should use a positive in here, which I will. Okay, so let me just substitute that here. I'll get negative I of S plus 1 divided by R. I think that will be L divided by R, DIL of T divided by D of T plus IL of T equals 0. I'll do a little bit of algebra, and I'll end up with DIL of T divided by D of T plus 1 divided by L divided by R in here. IL of T equals IS divided by L divided by R. And this here is of this shape dx of t divided by d of t plus 1 divided by tau x of t equals some sort of a kappa, okay, which is a constant. This is actually the differential equation that describes this step response of a first order circuit, first order RL circuit. And of course, tau is just simply L divided by R, similar to the natural response of an RL circuit. So we can find the solution for this differential equation by first I will just basically get I of L and its partial derivative on one side and all the other terms on the other side. So what I'll end up with is DIL of T divided by D of T equals just simply 1 divided by L divided by R, and that will be simply I of S minus IL of T, okay? Or we can just basically say this is minus, this is plus, and this is minus in here. So we'll have the I of L of T divided by simply IL of T minus I of S equals negative 1 divided by L divided by R, and that's here is D of T. We take the integral of both sides, so what we'll have is dy divided by y minus I of S, and that's basically from IL of T0 all the way to IL of T, and equals negative 1 divided by L divided by R, the integral from T0 all the way to T of d of x, and that integral will end up with the natural logarithm of IL of T, okay, divided by IL of T minus I of S, and I believe there will be a negative I of S in here as well, and that will be T0 in here, okay, equals negative 1 divided by L divided by R, and that's T minus T0. We take the exponent of both sides, we'll have IL of T minus I of S divided by IL of T0 minus I of S equals e to the negative 1 divided by L divided by R, T minus T0. All right, and I'll isolate IL of T, and you'll see that it's simply I of s plus IL of t0 minus I of s e to the negative L divided by R t minus t0. And that's basically for t is greater than or equal to 0. I can clean it up a little bit and I can basically say, well, IL of t0 is basically the initial current flowing through this. So if I assume that to be I0, which is just simply IL evaluated at t0, we can just basically substitute it by saying it's the initial current. So we can say that this is simply I0 minus I of s e to the negative, we can just write it tau or L divided by R, and that's t minus t0, and that's IL of t, and that's exactly t is greater than or equal to 0. So it's equal because the current doesn't change right before or right after that. And you can see it by substituting t, for example, to be t0, for example. You'll see that this here becomes the whole thing, because, well, the whole thing becomes 0, so e to the 0 is 1, and you can see that that becomes I of s plus I0 minus I of s, which is just simply I0. Okay, so which is fine. All right, so we found out the current through this inductor. We can just simply find the voltage across the inductor just by using this equation in here. Okay, so let me just write it down. Using passive sign convention tells me I have to use the positive, so simply VL of t is just simply positive L times the derivative of that equation that is highlighted in pink, which is 0, and that's negative 1 divided by L divided by R, I0 minus I of s, e to the negative 1 divided by L divided by R, t minus t0. Okay, and we multiply all of these, and what we'll end up with is the following. We'll end up with, I believe it will be negative R I0 minus I of s e to the negative 1 divided by L divided by R, t minus t0, and that's basically the L of t, which is in t is greater than 0, exactly greater than 0, not greater than or equal to 0. Because if you think about it, right before switching, even if we have current flowing through it, right before switching, that acted as a wire, so the voltage across it is 0. Right after that, it becomes not 0. If you want to get the exact value, just substitute t equals t0 and so forth. We can plot these. We can do a few assumptions in here. For example, we can just say, well, let's assume that the initial current is 0, and we can say that the t0 is 0, and we can substitute IL of t equals I of s negative I of s e to the negative 1 divided by L divided by R of t, and then of course VL of t equals simply negative R times negative I of s, that's positive I of s e to the negative 1 divided by L divided by R of t. And you can plot these, and what you will see is the following. So we can do this here. This is the x axis, which is just simply t. This is the y axis. We're going to say, well, this is I of L of t. So we'll start initially by saying, well, right before switching, when t happened to be right before switching is 0, well, the current flowing through it happened to be 0 in this particular case. And we said that because the initial current was 0, so we can say that it's 0. And the inductor opposes a change of current, so there should be no jump. But eventually, what will happen when t goes to infinity, the whole term in here goes to 0, so that basically tells me that you have to reach I of s in here. So what it does, it actually reaches that exponentially. That's what happens in here, because I'm charging that I'm charging that inductor. Similarly, we can take a look at the V of t. V of t initially happened to be 0, okay, but then we allow a jump, and that jump becomes, well, when t is 0, this is 1, so I of s times r, okay, so I of s times of r, maybe it's here, I s times r. So what happens, like, the current actually goes all the way to that value, and eventually you'll see when this goes to infinity, so the whole thing goes to 0, so that slowly reaches 0 in here, because that's basically the voltage. Remember, it's like this is here is the voltage, because we know that the VL of t eventually will go to 0, because eventually, if you wait for a very long time, this here will act as just a wire, so the voltage across it is 0, and that's what we see in here.